In 1942, American aircraft factories faced an invisible crisis. Nickel supplies tightened sharply as armor and naval production received priority, forcing the aircraft industry to conserve and substitute wherever possible. Engineers had months to redesign decades of metallurgical practice or watch production collapse. Nickel, a silver-white metal extracted from the Earth's crust. For nearly a century, it had been the foundation of industrial strength. Blended into steels, cast into engine blocks, forged into components that could withstand heat, stress, and corrosion. But when global war severed supply lines and redirected resources toward armor and munitions, availability became constrained. What remained was a question. Could American industry build an air force with sharply reduced nickel allocations? Nickel entered industrial consciousness in the mid-19th century. Chemists had known of its existence since the 1750s, but extraction remained impractical until Swedish metallurgist Axel Fredrik Cronstedt isolated the element in its pure form. For decades, nickel existed as a curiosity, a metal with interesting properties but no clear application. That changed in the 1880s. Metallurgists experimenting with steel composition discovered that adding small percentages of nickel to iron-carbon alloys produced dramatic improvements. The resulting steel resisted corrosion. It maintained strength at elevated temperatures. It could be hardened through heat treatment while retaining ductility. These characteristics made nickel-steel alloys ideal for applications requiring both durability and precision. The first commercial nickel mines opened in New Caledonia in the 1870s, followed by larger deposits discovered in Sudbury, Ontario in 1883. The Canadian deposits proved vast, containing enough nickel to supply industrial demand for generations. By the turn of the 20th century, nickel production had become a strategic industry, concentrated in the hands of a few mining corporations that controlled access to the metal. The early 20th century witnessed nickel's transformation from specialty additive to industrial necessity. In 1913, English metallurgist Harry Brearley developed the first practical stainless steel, an alloy containing chromium and nickel that resisted rust and oxidation. The invention revolutionized manufacturing. Stainless steel found immediate application in cutlery, surgical instruments, and chemical processing equipment. Simultaneously, the automotive and aviation industries recognized nickel's value in engine construction. Internal combustion engines generated intense heat and mechanical stress. Nickel-chromium alloys could withstand these conditions without warping or fracturing. Engine blocks, cylinder heads, crankshafts, and valve components increasingly incorporated nickel-bearing steels. The mining industry expanded to meet demand. By the 1920s, the International Nickel Company, later known as INCO, dominated global production, controlling approximately 90% of the world's nickel supply. The company's mines in Sudbury, Ontario, produced hundreds of thousands of tons annually, shipping refined nickel to steel mills and fabricators across North America and Europe. During this period, metallurgists developed standardized alloy compositions. The American Iron and Steel Institute and the Society of Automotive Engineers established classification systems for steel alloys, designating specific nickel content percentages for different applications. Alloys containing 8 to 20% nickel became standard for high-strength applications. Aircraft manufacturers, in particular, relied on nickel-steel alloys for landing gear, engine mounts, and structural fittings subjected to repeated stress cycles. The aviation industry's relationship with nickel began in the 1920s. Early aircraft constructed from wood and fabric gave way to metal designs as engineers pursued greater speed, range, and payload capacity. Aluminum became the primary structural material due to its lightweight, but aluminum alone lacked the strength required for critical components. Nickel-steel alloys filled this gap. Landing gear required materials capable of absorbing impact forces during touchdown. Engine mounts needed to secure power plants weighing hundreds of pounds while dampening vibration. Control surface hinges, wing attachment fittings, and tail assembly joints all demanded alloys that combined strength with fatigue resistance. By the mid-1930s, aircraft designers had standardized on several nickel-containing alloys. Nickel-chromium molybdenum steels provided exceptional tensile strength and could be heat-treated to precise hardness specifications. Stainless steels containing 18% chromium and 8% nickel resisted corrosion in marine environments, critical for naval aircraft operating from carriers. Engine manufacturers depended even more heavily on nickel. Exhaust valves operated in environments exceeding 1,400 degrees Fahrenheit. Turbocharger components withstood both extreme temperatures and rapid pressure changes. Nickel-based alloys remained essential in the hottest engine components, especially exhaust valves and turbocharger hardware, where no substitute could match their high-temperature strength. As aircraft performance increased, so did nickel consumption. A single radial engine for a military bomber contained dozens of pounds of nickel-bearing steel. Multiply that across thousands of aircraft, and the strategic importance of nickel supply became evident. Throughout the 1930s, the global nickel industry operated as a peacetime commodity market. Canada supplied the majority of the world's nickel, with smaller contributions from New Caledonia, Russia, and scattered deposits in Finland and Greece. The supply chain functioned smoothly. Mines extracted ore, refineries processed it into pure metal, and manufacturers purchased quantities as needed. American industry consumed substantial nickel tonnage annually. Beyond aviation, the metal found use in automotive manufacturing, railroad construction, chemical processing, and electrical equipment. Steel mills blended nickel into structural steel for bridges and buildings. Factories producing kitchen appliances used stainless steel containing nickel. The metal had become embedded throughout the industrial economy. European rearmament in the late 1930s created the first supply pressures. Germany, preparing for war, attempted to stockpile strategic materials, including nickel. Britain and France increased military procurement, drawing down available supplies. The United States, still officially neutral but expanding its own defense production, began competing for the same limited output. When war began in Europe in September 1939, nickel supply chains fractured. Germany controlled neither major mines nor refining capacity, forcing reliance on limited domestic deposits and seized Norwegian production. Britain prioritized nickel for armor plate and naval construction. The Soviet Union, possessing its own mines in the Urals, ceased exports. Canada's production became the primary source for the Allied powers, and demand far exceeded peacetime capacity. The United States entered this increasingly constrained market. Between 1940 and 1941, American aircraft production accelerated under the expanding preparedness program. Factories that had built dozens of planes monthly now planned for hundreds. Each aircraft required nickel-bearing components. Each engine demanded nickel steel valves and superalloy parts. The mathematics of mobilization revealed an uncomfortable reality. Available nickel supplies could not sustain the planned production increase. The Japanese attack on Pearl Harbor in December 1941 transformed nickel scarcity from concern to crisis. The United States declared war on Japan, then Germany and Italy. Military production targets increased by orders of magnitude. The aircraft industry received orders for tens of thousands of fighters, bombers, and transport planes. Naval shipyards began constructing hundreds of warships, each containing tons of nickel-bearing armor plate and structural steel. The War Production Board, established in January 1942 to coordinate industrial mobilization, immediately confronted the nickel shortage. Surveys of available supplies and projected consumption revealed a gap that could not be closed through increased mining alone. Canadian production could be expanded, but new mines required years to develop. Existing refineries operated at capacity. The board issued its first nickel conservation order in March 1942, restricting civilian use. Stainless steel for consumer products ceased production. Automotive manufacturers received reduced allocations. But restrictions on civilian consumption freed only a fraction of required supplies. Military demand continued rising. Aircraft manufacturers received priority allocations, but even those proved insufficient. Engine builders reported delays as nickel steel forgings became unavailable. Airframe manufacturers stockpiled landing gear components, uncertain when replacements could be obtained. Production schedules began slipping. The crisis demanded immediate solutions. Engineers could not redesign engines or airframes from scratch. That would require years of testing and certification. Instead, they needed substitute materials that could replace nickel-bearing alloys in existing designs with minimal modification. The War Production Board's Conservation Division initiated a nationwide substitution program in spring 1942. Metallurgists from steel companies, aircraft manufacturers, research laboratories, and universities joined the effort. Their mandate: identify or develop alloys that could match nickel steel performance while using little or no nickel. The challenge proved complex. Nickel contributed multiple properties to steel alloys. It increased hardenability, allowing through hardening of thick sections. It enhanced toughness, particularly at low temperatures. It improved corrosion resistance. It stabilized certain crystal structures in stainless steels. No single substitute element could replicate all these effects. Engineers pursued multiple parallel approaches. The first focused on chromium-molybdenum steels. These alloys, containing chromium and molybdenum but minimal or zero nickel, had existed since the 1920s but had been overshadowed by nickel-bearing grades. Metallurgists recognized that with proper heat treatment, chromium-molybdenum steels could achieve strength levels comparable to nickel steels. The alloy designated SAE4130 emerged as the leading candidate. This steel contained approximately 0.30% carbon, 0.80 to 1.10% chromium, and 0.15 to 0.25% molybdenum with no nickel. In the annealed condition, it possessed moderate strength, but when normalized and tempered, heated to 1,600 degrees Fahrenheit, air-cooled, then reheated to 1,100 degrees, 4,130 steel achieved tensile strengths exceeding 90,000 pounds per square inch, matching many nickel steel grades. Engineers scaled up and requalified chromium molybdenum steels such as SAE4130 as substitutes for traditional nickel steels. Aircraft manufacturers began substituting 4130 steel for nickel-bearing alloys in tubular structures. Fuselage frames, engine mounts, and landing gear struts could be fabricated from 4,130 tubing with minimal design changes. The material required careful welding procedures and heat treatment protocols, but fabricators adapted quickly. Simultaneously, materials scientists developed manganese-enhanced steels. Manganese, more abundant than nickel, provided some of nickel's beneficial effects when used in higher percentages. Alloys containing 1.5 to 2.0% manganese showed improved hardenability and toughness. While not equivalent to nickel steels in all properties, manganese steels proved adequate for less demanding applications. In aluminum alloys where nickel had been used to improve elevated temperature strength, metallurgists reformulated compositions using copper, magnesium, and zinc to reduce reliance on strategic nickel. The resulting alloys sacrificed some high-temperature capability but remained suitable for airframe structures operating below 300 degrees Fahrenheit. Translating laboratory developments into factory production required unprecedented coordination. The War Production Board distributed technical bulletins detailing substitute alloy specifications and heat treatment procedures. Steel mills reformulated production schedules to supply the new grades. Forging shops and machine shops received training in processing unfamiliar materials. Aircraft manufacturers revised specifications and drawings. Engineers reviewed every component containing nickel-bearing steel, assessing whether substitutes could be used. Landing gear received particular attention. The high-strength, high-impact requirements made substitution challenging. Through iterative testing, 4,130 chromoly steel replaced nickel-bearing steels in many structural tubes, engine mounts, and landing gear components where testing proved it could match performance. Engine manufacturers faced greater constraints. Nickel-based alloys remained essential in the hottest engine components, especially exhaust valves and turbocharger hardware, where no substitute could match their high-temperature strength. The War Production Board allocated scarce nickel supplies to these critical applications while pushing substitution in less demanding engine parts. By late 1942, substitute alloys had entered production. Fighters and bombers rolled off assembly lines with 4,130 chromoly steel, replacing nickel steels in fuselages and tail sections. Transport aircraft used manganese-enhanced steels for cargo floor fittings and door hinges. Trainers incorporated aluminum alloys reformulated without nickel in wing spars and control surfaces. The substitution program did not eliminate nickel consumption. Critical applications still required it, but reduced demand sufficiently to prevent production bottlenecks. Factories maintained output schedules. The bomber streams over Europe and the Pacific grew steadily through 1943 and 1944, supported by materials science innovations invisible to observers but essential to victory. The wartime substitution program's effects extended far beyond 1945. Chromium molybdenum steels, promoted from niche applications to widespread use under crisis conditions, proved their value. Post-war, 4,130 chromoly steel became a staple of aviation and automotive engineering. Aircraft manufacturers continued using chromoly tubing in light aircraft fuselages and helicopter airframes. The material's combination of strength, weldability, and relatively low cost made it ideal for structures where weight savings justified fabrication complexity. Thousands of small aircraft built in the 1950s through the present day employ 4,130 steel. The automotive industry adopted chromoly steels for high-performance applications. Racing car chassis, roll cages, and suspension components used 4,130 and similar alloys. Motorcycle frames incorporated chromoly tubing. The material's reputation for strength and toughness, established during wartime aviation use, transferred to civilian applications. Materials science as a discipline emerged from the war transformed. The intensive research into alloy substitution demonstrated that systematic investigation could rapidly develop new materials for specific requirements. Post-war universities expanded metallurgy programs. Government laboratories continued materials research. Industry invested in research and development departments focused on advanced alloys. The techniques developed for analyzing and predicting alloy properties became foundations for computational materials science. Metallurgists had learned to correlate composition, heat treatment, and resulting properties with increasing precision. This knowledge, combined with post-war computing technology, enabled theoretical prediction of material behavior before expensive experimental programs. Nickel supply concerns receded after 1945, but never entirely vanished. The Cold War created new strategic materials anxieties. Mining companies expanded production in Canada, Australia, and eventually Indonesia and the Philippines, diversifying supply sources. But the memory of wartime shortages influenced industrial planning. Companies maintained broader material qualification databases, ensuring alternatives existed for critical alloys. The aluminum alloy innovations likewise persisted. Wartime formulations without nickel proved entirely adequate for most applications. Post-war commercial aircraft used these alloys extensively. The Boeing 707, Douglas DC-8, and subsequent jet airliners employed aluminum alloys descended directly from wartime substitution research. The story of nickel shortages and substitute aircraft alloys illustrates industrial adaptation under existential pressure. For decades, nickel had been incorporated into countless applications because it worked well, not because it was irreplaceable. War revealed that dependence and forced examination of alternatives. Engineers discovered that other combinations of elements could achieve comparable results. Chromium and molybdenum could provide strength and hardenability. Manganese could enhance toughness. Careful heat treatment could compensate for compositional differences. These discoveries did not make nickel obsolete. It remained valuable and widely used, but they expanded the palette of available materials. The innovations emerged not from leisurely academic research, but from compressed development timelines and urgent production requirements. Metallurgists worked with incomplete data, limited testing time, and factories demanding immediate answers. That solutions emerged at all testifies to scientific understanding accumulated over previous decades, and the ability of engineers to apply fundamental principles under pressure. The legacy extended beyond specific alloys. The substitution program demonstrated that strategic materials vulnerabilities could be addressed through systematic research and rapid implementation. Post-war industrial planning incorporated this lesson. Materials science became recognized as essential infrastructure, requiring investment and attention even during peacetime. Today, chromoly steels and the aluminum alloys developed during that period remain in production, their origins largely forgotten by those who specify and use them. They exist as footnotes in materials handbooks designated by alphanumeric codes that reveal nothing of their history. Yet they represent a moment when necessity forced innovation and innovation reshaped an industry for generations to come. Watch next to see how America's wartime aluminum scrap drives connected ordinary households to industrial science and aircraft production.